All right, welcome back, everybody. Hope you guys had a safe and restful weekend. So today we're going to pick up our conversation of recursion. This is a new topic that we started exploring together last week, and we're going to continue exploring today. And we'll have more chances to use recursion in the future. You guys are working through a pretty serious set of problems on the homework having to do with recursion on trees, but we'll also look at recursion in a couple of other contexts as well. And so today's goal of today's class is to come together to look at, go over a problem using recursion together. It's a little bit more complicated than the ones that we've seen so far. It has a little bit of a different pattern. But we'll also introduce the idea of recursion as a broadly applicable problem-solving technique that we can actually use on data structures that aren't trees, because there are other recursive data structures and there's other problems that have a structure that lends them to more of a recursive approach. All right, and in particular, what we'll see, one of my favorite algorithms is we'll look at how to reverse a linked list using recursion. And that's assuming that I could actually get this right on camera, because I didn't practice this morning, and this is one of those algorithms actually pretty tricky to work in a live setting. So we'll see. Maybe today will be a little bit more of a train wreck than usual. All right, so again, hope you guys have a good weekend. MP4 checkpoint was due. I noticed that people were working on that and seemed to do pretty well. So you guys have one more week on the MP for this class. That's it. This journey that we started at the very beginning of the semester, where you guys started working on the first checkpoints, is about to end. It's about to, you guys are about to kind of climb all the way to the top and get to the summit of this particular mountain. And I know the course staff and myself are really proud of you guys for coming all this way, and particularly for continuing to work hard over the past couple weeks under very changed and difficult circumstances. All right, so recursion is, again, one of these concepts that is difficult to understand at first. And it's because there's, something strange about the idea of, taking a problem and then solving a smaller version of the same problem. It feels like, how does this end, And when we start to look at the code together, there's also some aspects of the code that makes recursive calls that can be a little bit weird to think about. And like everything else you've learned in this class, the only good advice I have for you here is to practice. And to practice some more. And at some point, this will start to sink in, and you will start to be more comfortable, not only with designing recursive algorithms, but also with thinking about how to solve problems in recursive ways, right? So not only thinking about how to solve problems recursively, but also recursive implementations of those approaches. So here are 3 strategies I think will help most of the time you approach any sort of problem where you're thinking about applying a recursive strategy. So remember, the core of recursion is that we make a problem smaller. And if you don't make the problem smaller, the problem, you're never going to get to a solution, but you also have to know when to stop. At some point, there has to be a problem that you can solve trivially. If you don't have that feature, then even making the problem smaller isn't going to help, because you're never going to get to a problem that's so small that it's so easy to solve that you can just stop. So when we counted the number of nodes in the tree on Friday, the problem that was so simple that we could stop, there were 2 variants of it, right? So the first one was we got to a leaf node, because at that point we know that the number of nodes in the tree rooted at that node is 1. Alternatively, we also programmed up a different variant of that same approach, where our smallest problem was actually getting to an empty tree, because we know that an empty tree has 0 nodes. So if we walk to the point where the node that we've arrived at is actually null, that means that the tree below that node is empty, meaning it has no nodes or 0 nodes, and so we return 0 in that case. So remember, we looked at 2 different approaches to recursive tree node counting. One of them, we stopped at leaf nodes, and that one had a little bit of extra complexity to it, because it turns out when you stop at leaf nodes, you have to make sure that you handle null cases within the body of that recursive function. Alternatively, we allow ourselves to walk off the tree to a null node, which means that we reach an empty tree. And that made the body of our recursive implementation much, much cleaner and more elegant. So that was the solution that we preferred, the one that we came to towards the end of class together on Friday. So at some point, when you're breaking the problem down to smaller pieces, you have to stop. You have to get to a problem where your strategy shifts from breaking the problem into smaller pieces to just solving the problem. Right? Obviously, if your strategy is always to break the problem into smaller and smaller pieces, you will never stop. You'll never get to a piece that's so small that now you can start building up your solution. We refer to this as the base case. And a lot of times when you look at recursive implementations of algorithms, the base case is the first thing that you see. So it's right at the top. And you saw that in our implementation of recursive tree counting. The first thing we did in both of our implementations was handle that base case. Handle that case where my strategy is not to make the problem smaller because I've arrived at the smallest possible problem. So in one case, that was checking to see if the node was a leaf, if both of its children were null. In the other case, that was checking to see if the node itself was null, meaning that I've reached an empty tree. So handle the base case. Whenever you write a recursive algorithm, that should be kind of step number one. Think about what is the place that I'm going to? What's the destination I'm trying to arrive at? If I make this problem smaller and smaller and smaller, what's the smallest version of the problem where I stop, don't make the problem any smaller, and start to create a solution? The next thing is you have to make the problem small. So you have to have this base case that you're going to reach. But your algorithm also has to be making progress in reaching that case. So if the algorithm is then actually making the problem smaller in each step, then it's never going to terminate. And again, last time we looked at a couple of cases with recursive tree counting where if I didn't make the problem smaller, I would run into this characteristic stack overflow error. And that error is the error that you get almost always when there's some problem in your recursive algorithm and you're not actually making the problem smaller. So on a tree, the typical way that we make the problem smaller, and we'll see this again later today when we go over a problem together, is we look at the right and the left subtree separately. So it's worth thinking about, again, and reminding ourselves, why do these constitute smaller problems? They constitute smaller problems because at any point in the tree, if the tree has finite size, if I think about the current problem I'm trying to solve, which is the tree rooted at the node that I'm at, okay, that tree has some number of nodes. The left subtree and the right subtree are both smaller than the tree that's rooted at the node that I'm at. Sometimes they're only a little bit smaller, but they're both definitely smaller. And so if I can break the problem down into doing something with the left subtree and doing something with the right subtree and combining the results, I've created two smaller problems. And if I can keep doing that, what's going to happen is those smaller problems are going to get smaller and smaller and smaller, and eventually I'm going to reach that base case. So you can think about counting a tree with lots and lots of different nodes. I start at the top. I look at the left and right subtree. Those are still pretty big problems. Then I look at the left and right subtree of the left subtree, and those are still pretty big problems. And I keep doing this, but eventually I get all the way down to the leaf nodes of the tree, and now I'm looking at very, very small problems. So eventually, if I apply a good strategy for making the problem smaller, I will arrive at the base case. And the third step, the third element to this, is really figuring out how to combine the results from the two smaller problems. This varies a lot based on what problem you're trying to solve. So when we look at trees, our typical base case that we're going to use is an empty tree. That's what we reach when we walk off of the bottom of a leaf node or off the side of a node that doesn't have a right or left child. And that's where we're going to stop typically. We're going to stop when we reach an empty tree. The recursive step, or making the problem smaller on trees, is typically looking at the right subtree and the left subtree. So those are the same for a lot of the problems that we work with on trees. What's different is how we combine results. So we have some data that we've gathered from the right subtree and some data that we've gathered from the left subtree, and we need to figure out how do we combine those two results together to produce a solution for the larger problem. When we did tree counting, again, going back to last Friday, what we did is we counted the number of nodes in the right subtree, and we counted the number of nodes in the left subtree, and we added those together, and then we added one for the node that we were at, and that was the count of the nodes in the tree rooted at the current node. So we used addition to combine the results from our right subtree and our left subtree. Today, when we look at a different problem, we're going to combine those results differently. We're going to use a different approach. Okay. We also looked a little bit at a different form of recursion, and this is something that we'll continue today. We'll look at a couple of places where we can use recursion to solve problems. So in this case, we looked at factorial, a recursive implementation of factorial. Factorial is defined as, factorial actually has a recursive definition, which is that the factorial of n is equal to n times the factorial of n minus 1. And like our recursive algorithms, the recursive definition also has a base case, which is that the factorial of 1 is 1. And so the idea is if I give you any number, you can compute the factorial by applying that definition over and over and over again on smaller and smaller numbers until you eventually get to 1. So here was our implementation of recursive factorial. And whenever we look at a recursive algorithm or the implementation of a recursive algorithm, we should be able to identify the different parts. So in this case, the base case is right here. It's the case where n is equal to 1. And you can see many times in the base case, what we do is we just return an answer right away. We don't make a recursive call. We don't call the function again. We stop doing that, right? And we return some information. With our node tree count, we returned 0 if we were walking to the empty tree, because that's the number of nodes in an empty tree. Here we're returning 1 because the definition of factorial says that the factorial of 1 is 1. Otherwise, what's my recursive step? So here, the recursive step is making the problem smaller. So if I don't solve the problem immediately, if I haven't reached the base case, then what I need to do is I need to make the problem smaller somehow. How do I do that? In this case, I make the problem smaller by calling factorial of n minus 1. So given a large number n, what we're doing is we're turning this into computing the factorial of a slightly smaller number. And if we do that over and over again, eventually we'll get to the case where n is 1, and we can immediately return the result. And the way that we combine the results here is by multiplying, and this is because of the definition of factorial. The definition of factorial says the factorial of n is n times the factorial of n minus 1. And so we're combining results according to the definition of factorial. Now, one of the problems that we noted with this, or this is sort of a question I left you with at the end of class on Friday, was what happens if we don't reach the base case? So in this example, you can see that there is a case where I don't reach the base case. And you might think about this for a minute, but I'll go on and show you what happens. So if I try to compute the factorial of -4, okay? So let's actually just put a print statement in here so that we can see what's happening. So let's just print n at the top. And you'll see, oh, I have this long stack trace. I don't think I'm going to get any output from this thing. So it turns out if you were able to print this, what you would see is, factorial, the implementation that we have here, says, okay, well, you asked me to compute the factorial of -4. I don't know how to do that, but I do know that that's -4 times that factorial of -5. And so now I need to compute the factorial of -5. Okay, well, how do I compute the factorial of -5? Well, you told me that the factorial of -5 is -5 times the factorial of -6. And this keeps going and going and going and going and going. And it will never actually get into this case because I started with -4 and I'm going down. And so I'm going into smaller and smaller numbers and I'm actually never going to reach the case where n is equal to 1. So it turns out the factorial is not defined for negative numbers, right, for this reason. And so the right thing to do here is to essentially say, if n is negative, we should, we should return some number that indicates that I wasn't able to compute the factorial because you gave me an invalid input. But this is a simple example of a recursive algorithm that has this common bug that you guys, I would be willing to bet that most of you, before you are done with this next series of homework problems, are going to encounter a Stack Overflow error at some point, right? If you don't, congratulations. If you do, you're normal. This is, how you learn, because it's pretty common to get into a case where either, in this case, I miss the base case, or I'm not actually making the problem smaller. And so the problem, keeps being the same size, and I keep trying to solve it by solving a problem the same size over and over, and eventually the program is going to run out of memory and crash. And again, this is sort of the characteristic error message that you get here when you don't when you don't finish in some number of calls, right? Okay, so again, it's not good. Now, last thing I left you with on Friday, and I do want to reiterate this, is just this idea that recursive solutions, at least when you're starting out, can be difficult to understand. And our goal, as always, is to write clear, concise, readable, understandable code. It's not to show off, it's not to use a particular technique, it's not to reduce the number of lines of code to 0. As you go along and learn and grow as programmers, you will start to develop some intuition about certain problems where you need to use recursion and other problems where you don't. Again, there are always ways to use recursion to solve every problem, and you can always solve every problem using an iterative approach as well. The question is, what's the right approach? And this becomes a question of design and aesthetics. It can be influenced by the language you're working in and how well it supports recursion and other things, right? But the goal here is not to use one technique over another for the purposes of using a technique. It's what's the right tool for the job? What's the approach that's going to fit in best to what I'm doing, to the rest of my code, but it's going to actually solve the problem in an elegant way that I can understand when I go back and look at later, and that other people that might be working with me on the code can also understand and appreciate. That's the goal, right? It's never to just use recursion because it's like, oh, nobody understands recursion, and I think I understand recursion, and I'm cool because that's, there are cooler ways to be cool than using recursion. And again, line count is not a proxy for clarity. That's something that, maybe if I say it and Mike Woodley says it and Carl says it and Mariana says it, maybe we'll actually drill this into your heads. Writing fewer lines of code is not the goal when building a software project. It's to build something that's maintainable, that's understandable, and that solves the problem. If you can do that with writing fewer lines of code, great. If it takes more, but those are good lines that make your solution and your algorithm easier to understand and appreciate, then by all means do that. Because again, here's our iterative approach to factorial. And this, for some of you, this will be the more intuitive approach. For others, you'll like the recursive approach. In this case, the recursive implementation of factorial, on some level, is a better match for the definition of factorial, which is itself recursive. But both of these pieces of code do the exactly same thing and produce the exactly same result. All right, so now let's solve some problems together. And this is one of the ways that, both in class and on the homework, we're going to build up your capacity to use recursion to solve problems. Okay, so the first thing we want to do is we're going to pose a problem. Typically, at least for today, I think we'll look at a mixture of things, but over the next few homeworks, you'll be using recursion largely on trees. You will have an opportunity later when we talk about sorting to use recursion on arrays as well, where it's also an interesting fit. But for now, we're using it on trees. And so here's our goal. Given a tree of the kind that you guys have already been working with, let's print the values of the leaf nodes. Okay, so leaf nodes are nodes that don't have a left or a right child, right? So whenever we start thinking about this, we want to think, what's a recursive algorithm? And let's identify the three parts of our recursive algorithm, okay? So what's the base case here? What's the point at which I need to... So on some level, you can think of this as this algorithm as having two parts, right? One part is I'm searching for leaf nodes. So I need to find the leaf nodes. And then when I arrive at a leaf node, I'm actually going to print the value as well, right? But really on some level, what we're doing is we're writing a function that searches for leaf nodes. So what's my base case? My base case is I've reached a tree that has no left or right node. That's a leaf node, okay? So at that point, I'm going to print the value of that node. Now, the nice thing about this is that once I get to a leaf node, there are no other nodes to look through. And so I'm done, right? I can essentially stop at that point. My recursive step, as it typically is when I look at recursion on trees, is to make a problem smaller. If I'm at a particular point in the tree and I'm not at a leaf node, then what I'm going to do is I'm going to say, okay, well, I've got two smaller problems to solve now. I need to print all the leaf nodes in my right subtree and all the leaf nodes in my left subtree. And once I do that, I'll print all the leaf nodes in the tree rooted at me, at this node. And the way that we combine the results, in this case, there's really not much here to do because the way that the results appear is by being printed. So the way I combine results, I don't really need to do anything special. I just run the algorithm on the right side of the tree, run the algorithm on the left side of my left subtree, and that will just do the right thing. Okay, so here's our favorite binary tree class. It has all the usual features, and I've left a little spot here for us to work on this print leaves function. Okay. Now, similarly to how we did this when we counted, a lot of times when we expose this function on our tree, what we're going to do is we're going to have a public function that returns void. And then what we're going to do is we're going to use that to call a private helper function that takes a node to print the leaves for. So essentially our private function is going to print all the leaf nodes in the tree rooted at a particular node. Okay? This is also how we're going to apply this function recursively. So now I have a function that prints all the nodes in the tree, the leaf nodes in the tree, but the way I'm going to actually get that to work is I'm going to call my print leaves function, and I'm going to start it on the root node. Now, like we did before, we can approach this in two different ways. So let's actually use the literal algorithm that we drew up there, which says the base case. And remember, whenever you're writing a recursive algorithm, I would strongly encourage you to start by writing the base case first. It's the first thing your function should do, is handle the case where it's reached a very small problem that it should be able to solve immediately. In this case, our very small problem that we should be able to solve immediately is I reached a leaf node, which is awesome. So if current.left is equal to null and current.right is equal to null, this node has no trees below it. It has no right child and no left child. And so I'm in a leaf node, and what I need to do is just print the value at that node. And remember, I'm printing the value, not printing the node, right? Each node in my tree contains a value. That's the data that we're storing in the tree. And so in this case, I'm going to print the value. So that's my base case. And then I also need to return, because at this point, I don't have any more work to do. I'm done. Okay, so now what do I need to do here? So if I'm not a leaf node, then I have either a right tree or a left tree. So let's handle those cases. So if this node has a right, a left tree, then I need to also print all the leaf nodes in that left tree. And so I'm just going to call print leaves on current.left. I need to do something very similar for the right subtree. I'm going to call print leaves current.right. Otherwise, that's it. I'm done. Remember, there's really no combining results here because I'm printing things as I go. And so that's how I expect the results to get to the tree. Okay? So let's see how if this works properly. You'll see that because the tree is created randomly each time, sometimes I have 2 leaf nodes, 4 and 3. Sometimes I only have 1 leaf node, right? How can this tree only have 1 leaf node? Well, what if I have a root node, which is 1, it has a child, which is 2, it has a child, which is 3, and it has a child, which is 4. That's essentially a linked list, just tilted over a little bit to look like a tree. But that's possible. From time to time when I build our tree, what happens is this tree only has 1 leaf node. Every tree has at least 1 leaf node, but I can always construct a tree that has only 1 leaf node. So in this case, sometimes I've got 2 leaf nodes, and the leaf nodes can either be 2, 3, or 4, depending on where the nodes exactly end up in the tree. So it's possible that, given different trees, the nodes 2 and 3 and 4 might end up at different places, and so any 2 of them can be leaf nodes. Now you might ask yourself, is it possible for all 3 of them to be leaf nodes? And in a binary tree, the answer is no. So in this case, if 2, 3, and 4 were all leaf nodes, that would mean that 1 would have to be their parent. And that would mean 1 would have 3 children, and it couldn't be a binary tree. So it's possible to have 2 leaf nodes. It's possible to have 1 leaf node. It's possible for any of the nodes with values 2, 3, and 4 to be a leaf node, but it's not possible for all 3 of them to be leaf nodes. Okay, so this is our solution. Now, like we did last time, we might want to check to make sure that this works in all cases, and it doesn't. So this is our bugaboo. It still doesn't handle this case where I have an empty tree. And why doesn't it handle that case? Well, when I have an empty tree, my root node is null. My root reference is null. And so when I get in here, I try to dereference that null reference, and things explode. And so what I really need to do is I need to put in another check here. I need to say if current is equal to null, then I'm just going to return. Right? Now what will happen is when I try to run it on an empty tree, it won't do anything. But it turns out, very similarly to how we did things when we counted the number of nodes in the tree, once I handle the null case, I don't have to check for null here. So what I can do is I can just do this. So essentially, I can print the number of nodes in my left tree, print the number of nodes in my right subtree, and this will now work for any number of nodes. Here I've got 2 nodes that are leaf nodes. Sometimes I could have 3 nodes that are leaf nodes. This is a 5-node tree, so that's okay. I added a node to it, but this algorithm still works. So again, let's go back and think about how we constructed this. So our eventual implementation is a little different than what we proposed here when we walked through the algorithm. So our base case, that we actually have 2 base cases here. One base case is I've reached an empty tree. In an empty tree, there are no leaf nodes to print, and so I'm done. And this could happen right away. If the root node is null, then what will happen is I'll reach an empty tree immediately, and I want to stop. Okay. Otherwise, what I do is I check to see if the current node is a leaf node. So if current is not null, then I'm actually at a node in the tree. How do I know it's a leaf? It doesn't have a right child or a left child. In that case, I print it, and I'm also done because I've reached a leaf node. I could actually get rid of this return statement and the code would still run. What would happen is when it got to the leaf node, it would print it, and then it would call print leaves on current.left, which is null, print leaves on current.right, which is null. Those would both start here, hit this null check, and return. But there's no point in continuing to look through the tree here for leaf nodes because once I reach a leaf node, I know there's no nodes that are farther down in the tree. Otherwise, if I'm at a node, I print the number of nodes in its left subchild and print the number of nodes in its right subtree, print the number of nodes in its left subtree, print the number of nodes in its right subtree. And I know that I can do this safely even if it doesn't have a left subtree or a right subtree. And the reason is I'm handling this null case right here. And so this is my recursive algorithm. And again, this is pretty slick, right? It's elegant, it's concise. It's not a huge number of lines of code in here. It does the job quite well. All right, I'm gonna flip over to the forum here just to see if anyone has any questions. Please do ask questions. I will take them. I know this is complicated stuff. All right, let's move on. Okay, so one of the things I want to talk about today, which is kind of an exciting point in the semester, is a new feature that we introduced at this point in the semester where we assign 1 point for each homework problem out of 10 for writing code that we consider to be quote unquote, there's a lot of quote unquote things today, right? Quote unquote class online, quote unquote perfect. And the goal here really is to, for the remainder of this semester, help you learn and grow as programmers by pushing you a little bit with just a little bit of an incentive, 1 point, not much, to write code that is better than some of the code you might have written before, okay? Now, look, no one in the course staff is looking at your code for the homework problem, so we can't tell if it's really perfect. There's all sorts of really terrible things you can be doing that we can't check for, right? You could be using terrible variable names. I've seen people do this now that I've started to jump on the help group and the help channel and look over your shoulder at your code. Some of you guys use awful variable names, like bad choices. Maybe they amuse you. That might be one reason to choose variable names. They've definitely amused me a few times. But we can't test things like this. But there are a couple things that we can test that will push you in the direction of writing code that is concise, beautiful, elegant, and quote unquote perfect. And so there's 2 things that we're going to look for. And I want to kind of explain what they are and explain why they matter. Okay, so 2 things. First of all, if your code contains code that is called dead. Dead code is unreachable. And in this context, it's also code that was never executed by the test suite. So what we do is we take your code, we run a bunch of tests, and if parts of your code were never executed during the tests, we consider that to be what's called dead code. Okay. The second thing is if your code is too complicated, it's too complex, and I will explain what this means. This is not calculated by line count, it's calculated in a different way. Okay, so let's first look at dead code, right? So dead code is code that for a particular set of inputs is never executed. The problem with dead code is simple. If your solution contains dead code, it can't be perfect. Why? Because I could take that dead code out and it would still work. And if that's the case, then it's not perfect. You've got stuff in here that isn't needed, it doesn't belong. right? So let's look at an example of some dead code. This goes back to the problem we did on Friday in class for tree size. I check to see if current is null, I return 0. And now I have this statement, I say if current is not equal to null, return 1 plus size, blah, blah, blah. So this is correct. But then I have this other return statement down here, okay? So what's wrong with this, right? Well, first of all, if current is null, I have already returned on line 7. So this piece of code down here can never be executed. There's no way for me to ever get into this if statement because I already checked whether current is null. So essentially, I can take out line 9, I can take out the rest of this if statement, and I can move line 10 over to the left, and the code is still correct. So this constitutes dead code. It's unnecessary, it's not helping you, it's not contributing anything, and it means your code is not perfect. Okay, so that's the number one thing we look for, dead code, you know? And again, we mean dead code from the perspective of the test suite, right? The test suite, so we describe the problem in English. We have a test suite that also behaves according to what we told you to do in the problem. And so if you have code that's not needed because the problem description didn't indicate that you needed to do that, then we'll still consider that dead. So a good example of this is, let's say that we told you the parameter, the argument we pass to your function will never be null, and you're checking for null. Well, that's dead code because when we test your code, we'll never pass null. And so you've got to check for null that never gets triggered. Now, again, we are very careful to explain what to do in those situations. We'll either say, if it's null, you should do this, or we'll say, we'll never pass you null. But that's a case where you might have code that you might think is useful, because it's like, what happens if somebody passed me null? But the problem description very clearly says we will never pass null to your function. Okay, so let's look at high complexity code. So here's an example. I think I actually took both of these from actual student submissions from a couple of years ago or whatever. So actually, the other thing I want to point out, it's really important. All this stuff's correct. We don't evaluate your code for perfection until it's correct. So you have to pass the test suite first. So perfection is distinguishing between two types of solutions. Solutions that are correct, but could be better, and solutions that, at least as far as we can establish, are very close to being completely perfect. So here's another example of something that's correct. This is, again, an example of counting the number of nodes in the tree. So I've got my base case here. That's perfect. And now what I'm doing is I've got this big if statement. So I basically say if current is left is equal to null, then I only check current.right. If current.right is equal to null, I only compute the size of current.left. Otherwise, I have this down here. If they're both not null, then I compute both. And again, this code just isn't needed because you're already handling the null case. So I can replace this whole if statement with just return this line on this line 14. So I can strip out all of this other code and replace it with just this one line, and it will still solve the problem. It's simpler, easier to understand, and easier for other people to maintain. The way that we measure complexity, and this is interesting. So this is a well-known definition of complexity. It's called cyclomatic complexity. It has to do with the number of different ways that when your code runs, the execution can flow through the function. So for this piece of code, there are 4 different code paths. One of them is if current is equal to null, at which point I return 0. The other one is if current.left is equal to null, at which I return this. The third one is current.right is equal to null, and I return this. The fourth one is this else statement at the bottom. So there are 4 different code paths. And the idea is when you're thinking about code and how to solve problems, the more paths there are through a piece of code, the harder it is to think about what's going to happen. You know, the fewer paths there are through a function, the easier it is to think about what's going to happen. So you might have a long function that does a lot of things, but if there aren't a lot of like conditional statements with returns and stuff like that, you're still just going like one thing at a time. So there's one path. In contrast, this is not a very long piece of code measured by line count, but it's complex because there's lots of different ways that the code can flow through this and do different things. And when you're trying to read code and understand it, that complexity turns out to be very problematic. Okay? For the solution to this problem, there were only two code paths. So remember, the solution was this up here that establishes one path if current is null. Otherwise, this return statement, which is used for all other cases. So here, the solution has a complexity of 2. Your code had a complexity of 4. This would be considered to be not perfect. It's not close enough to the solution. So I will take questions about our definition of perfection on the forum, and I'll be happy to kind of walk through. And the CAs will be happy to help you with this. Like, you can ask for help on on getting this extra 1 point, right, on each homework problem. That's totally legit. Okay, so let's go on and do a little bit more of a sort of an interesting problem that will stretch our legs even more at doing recursion on trees. So what we've done counting and we've done printing, but we haven't really done something that exercises our ability to do a couple of different aspects of recursive algorithms. And so recursive tree search is a fun one. All right, it's a fun thing to do, and we'll have another important question. Do the perfection points count on midterms and exams? No, they do not. It's only homework, right? If you can bang this out during an exam setting, more power to you. We're cool with that. So there are no points for perfection on the exams, any kind, quizzes or the final midterm. Great question. Should have had that as part of the slide. Sorry about that. All right, so let's do recursive tree search. Again, this is fun. So our goal here is, given a tree, to be able to determine whether or not it contains a certain value. So each node in the tree contains a value. And my goal is I'm looking for that value in the tree. Now, this algorithm has some new features to it that are going to, again, stretch us a little bit when it comes to thinking about how to use recursion in real settings. Okay, so let's go through this together and think about how to do it first of all, right? So what's the base case? So up until this point, our base case has been frequently when we get to the bottom of the tree, we get to a leaf node. That's when we stop. When we count the number of nodes in the tree, that's the right thing to do. When we need to print all the values of the leaf nodes, that's the right thing to do. But when we when we're looking for things in the tree, the base case is a little different. Okay, so the way to think about the base case is, when can you stop? When do you not have to make the problem smaller anymore? And in here, we can actually, I got ahead of myself, right? So for now, let's just approach this the way that we used to, and then we'll go and we'll optimize it a little bit. I'm sorry, I got so excited about this being cool that I kind of ruined the surprise. So so when we've reached a node that has an empty tree, or a node that has no descendants, so let's actually think about it this way. When we reach an empty tree, if we're looking for a value in a tree and we reach an empty tree, meaning that the tree we started with is empty, or we walked off the side of the tree or the bottom of the tree, what's the result at that point? False. An empty tree never contains the value we're looking for. It's impossible. It doesn't contain anything. What's the recursive step? Okay, well, I look in my right subtree and I look in my left subtree. That's my recursive step. So I basically say, okay, I'm going to search for the node in my right subtree and I'm going to search for the node in my left subtree. How do we combine the results? Well, I say the value is in the tree if it's in either my right subtree or my left subtree, right? So I'm looking for a particular value. If it's in my right subtree, it's in the tree, or if it's in my left subtree, it's in the tree. And so this is a logical operator. We're not using addition like we did when we counted. We're actually using a logical truth operator, right? Because if it's in either half of the tree, it's in the tree. Okay, so let's do this. Okay, so I've got a search function, right? For now this is another example of a case where now I'm passing a parameter to my recursive function. Okay, so my public search function takes this parameter. I'm going to do the same thing I did before, which is that I'm going to have a private search function that's going to take both the object, the value to look for, and a node to look, the tree to look at. And then what I'm going to do is I'm going to return search for value on the root. So the search function exposed by my tree class searches the entire tree starting at the root. All right, so let's construct our recursive algorithm. So again, always the case to start with an empty tree. To think about how to handle our base case in this case, which is if current is equal to null, then I'm going to return false. I've reached an empty tree. An empty tree never contains a value. So again, the root might be empty, in which case this tree has no nodes, in which case it never contains the value I was looking for. Okay. So now, let's apply a recursive algorithm. So there are three places actually I need to check. I need to check myself, my right subtree, and my left subtree. And it turns out we can actually do all of those in one very elegant statement. So if I've reached an empty tree, I stop. Otherwise, what I do is I say return current.value equals value. So the first thing I do is I compare my own value with the value. I'm using dot equals because this is an object, not a primitive type like an int or whatever. So there's three places where the value could be. It could be here with me, or it could be in my right subtree. So I'm going to search for the value current.right, or it could be in my left subtree, value current.left. I think checkstyle is going to be angry with me about this, so let's rewrite this to put in some line breaks, or. Okay. So three places I'm looking for the value. I'm looking at this node, the current node. So if the current node contains the value, then it's in the tree. Or I look in my right subtree, and I say if the value is anywhere in my right subtree, then it's in the tree. Or I look in my left subtree. If it's anywhere in the left subtree, it's in the tree. So let's see if this works. Check style. I don't want to use tab characters. I'm going to try to use space characters. Oop. And then I think it's bad about this too, probably. Oh, it's mad about this. Oh, okay. Oh, relax, Jess. This thought could be quite. I don't know what's wrong here. All right, there we go. Okay, so at least the first value I looked for seemed to work, but let's try some other values. Let's try a string. That's not in the tree. Let's try an integer that's not in the tree. Let's try another integer that's not in the tree. Okay, this seems to work. So this, again, like we just wrote tree search. That's like a canonical algorithm that people learn about, right? You guys just learn how to search through a tree. It turns like this is a little bit more sophisticated than we might think. And so to get a sense of exactly how cool this is, let's change our code a little bit and let's count the number of locations that we need to search for before we find the value or don't find the value. Okay. So what I'm going to do in order to do that is I'm going to add this public static int search count. And what I'll do is I'll have my wrapper function. Let me move this up here. My wrapper function set that to 0. So it'll say search count is equal to 0 before it starts the search. And then every time I get to a node, I'm going to set search count plus plus. So I'm going to increment the number of nodes. I'm not going to worry about these empty tree cases because technically I didn't arrive at a node. The question is, how many nodes do I have to visit in the tree before the algorithm finishes? So now let's do this, and now let's print off binary tree dot search count. All right, so here's what's interesting about this. Okay, so let's look at the first case. I'm looking for the node with the value 1. Now you might think that I need to search the entire tree. That's what I had to do when I counted. That's what I had to do when I went to the leaf nodes. I had to go through the entire tree. But it turns out our recursive search algorithm is smarter than that. And what we want to do for the next few minutes is just to look at why. What's happening here, right? Why is this working this way? Because it turns out if I search for the node 1 in this tree, I only visit one node. And that's pretty cool. Let's look at what happens if I search for a node that's not in the tree. Now, if I look for a node that's not in the tree, think about it. How am I going to be sure that the node's not in the tree? Well, I've got to go to every single node, right? I've got to start at the top, I've got to go to all the leaves, and I've got to work my way through every single node in the tree before I can be 100% certain that that node doesn't exist. If I don't visit every node, then it's possible that the node I didn't go to has the value I was looking for. And so whenever I do a failed search on a tree, in this search algorithm, it's going to have to visit every node, right? So if I look for 5, you're going to see it's going to go to 4 nodes. If I look for 10, it's going to go to 4 nodes. If I look for a value that's in the tree, it might not have to visit every node in the tree. And the question is, why not? So let's look at what happens, and let's think about this, because this really comes down to a logical OR. Remember, like what seems like years ago, we talked about how Java evaluates logical operators. And it does this thing called short circuit evaluation, which means it stops as soon as it knows the answer. That is playing a huge role in how our algorithm is working. Let's look at why. So let's say I'm looking for the node 1. Because of how we create our trees, we know that the first node in the array is always the root. So in this case, I'm looking for a value that exists in the root node. So I come in here into my search function and I say, is current null? No, because I'm looking at the root node. Okay? And now I get into this return statement. So this return statement has 3 parts, but they're separated by an OR. And so as soon as Java finds something that makes this true, it stops. And in this case, the first time I call this is the root node. Current.value is the value I'm looking for. So current.value value is true. And that means that these 2 parts of my OR statement never get executed. Remember we talked about how powerful short circuit evaluation could be? Here's one of the use cases for it, which is as soon as I find the node I'm looking for, I stop. Now, I can be a little bit dumber about this, right? So let's imagine that I set this up like this, which is not the right way to do it. You'll see why in a sec. So let's say that the last place I look is the current node, okay? So now what's going to happen? I need to put an extra semicolon down here. So my algorithm still works. But now, even when I look for a node that's in the root, it searches the entire tree. Why? Because I told it that the first place to look was in the right subtree, the second place to look was in the left subtree. So it looked in the entire right subtree, which might consist of like 2 and 3, didn't find it. Looked at the entire left subtree, which might consist of 4, didn't find it. And then only at the end looked in, on some level, the most obvious next place to try, which is the current node. So this has a lot to do with how I structure the state. So again, if I put this back to the correct way of doing it, then I get this really nice behavior because I find the value immediately. If I look for a value like 2, 2 could be one of one's children. In fact, 2 is, sometimes 2 is one of one's children, right? But so sometimes I find it, I look at 1 and then I find it immediately, but now it depends on whether or not it's in the right or left subtree. If 2 is in the right subtree, I'm going to find it quickly because that's the next place I look after I find that it's not the root node. If 2 is in the left subtree, you're going to see values like 4, because in that case, I'd look through the entire right subtree, and maybe the right subtree consisted of the nodes 3 and 4, and then finally I looked in the left subtree, and the left subtree consisted of the node 2. And so the behavior of this now depends on where the nodes are positioned in the tree. But the fact that I'm using this OR statement means that as soon as one of these evaluates to true, Java doesn't execute the rest of the statement. And so that gives me a big efficiency boost. All right. So now, and this is something that we'll come back to and talk about on Wednesday, because this is fun and it's cool, and it gives us a new way to think about how we use trees and a new variant of trees to experiment with for a little bit. You might wonder, how can we make this more efficient? And the answer is yes, we can. This starts to lead you down a path that leads to some very cool data structures that you'll work with in CS225 and in other classes that are variants of binary trees, and specifically a variant that's known as a binary search tree. And so I don't have time to get into this, and I think I'll come back to it and talk about it on Wednesday because it's a lot of fun. But the idea here is that what I want to be able to do in my search algorithm is I want to know whether or not I should look in my right subtree or my left subtree. Right now, because of how I construct the tree, the value could be anywhere. If the value isn't at my node, then I don't know whether or not it's in my right subtree or my left subtree. It could be in either. But it turns out, if I'm a little bit more clever with how I create my trees, then I can know whether or not the value should be in the right subtree or should be in the left subtree. And so we'll kick off on Wednesday talking about binary search trees. This is also fun because we get to bring the comparable interface back into things, and we get to see how we can make this search even more efficient by applying some rules when we create the tree and add items to it that make it easier to find items when we're looking for them later. All right, so I'm out of time for today. This is really fun stuff. I mean, I know that times are tough and there's a lot of scary stuff going out there in the world, but I hope you guys are enjoying these chances to look at some of these data structures and algorithms together. This is really cool material. It's a lot of fun for me to talk about. I hope it's as much fun to listen to, maybe a little bit less fun to listen to, but hopefully fun. All right, so again, on Wednesday, we have our next synchronous quiz at 10 a.m. or 6 p.m., depending on which one you're taking. There are questions on coders on this quiz, Chapter 7. Okay, so Chapter 8 we'll look at for next week. Chapter 7 for this week. So remember, we had the midterm last week. So this week's quiz focuses on algorithm analysis and lists. There are no questions on trees. We're a little bit for the next few weeks, the quizzes are kind of going to catch up with us. Right now, I want to evaluate you on the material we were talking about last week. And so the things we talked about today and Friday, the new tree material and recursion, those we'll get to on next week's quiz. On Wednesday, we're going to look at algorithm analysis, lists, the few programming problems we need to work on. Good luck on that assessment. I will live stream that day at 11 a.m. As for the rest of the semester, there's no participation taken, but hope at least a few of you will join me at that time. And I look forward to seeing you guys on the help system, on the forum. I hope everyone stays safe and well. Take good care of each other and the people around you. And I will look forward to being with you again on Friday.